Our world is so big that more than 7 billion people fit onto its surface, with room to spare. Even more astoundingly, our huge planet Earth is only a speck in our galaxy, the Milky Way. Now think about this. Everything in the enormous universe we live in is made up of atoms. Atoms so tiny that there are billions more atoms in a single salt crystal than there are people on planet Earth. At the University of the Free State, we use telescopes to reach far into space to learn about the structure of our universe. We are taking a journey deep into space, a journey into the heart of nebula. Huge clouds of dust and gas, the birthplaces of stars where atoms join together in a process of nuclear fusion. After billions of years, some of these stars will eventually explode into a supernova, a dramatic event with energy so great that it pushes atoms together to make all the elements of the known universe. Take a deep breath of air. Every atom you just breathed in was created inside a supernova like this one. With recent developments, the ability to work with individual atoms has brought us to the edge of a new frontier. And all these tiny atoms are extremely useful because atoms from different elements make up everything in the world we know.
Elements on a nanoscale have transform properties. Here at the University of the Free State, we are working to discover these properties and use them to positively impact people's lives.
This is the world of nanotechnology, where nanoparticles leave behind normal behavior and adopt the strange rules of the quantum world. New properties mean new applications, so the world of nanotechnology is like having a whole new periodic table at your fingertips. Every day we rely on this technology when we pick up our cell phones to make a call or watch sport on a flat-screen television. All the images on our flat-screen devices are made possible by nanotechnology. By combining light-emitting diodes of red, green or blue, we can create images of every color imaginable. Light-emitting diodes or LEDs contain nanomaterials called phosphors, which glow with different colors when they are exposed to an energy source such as ultraviolet light found in sunlight. Why do you think your new power-saving globe is white and not see-through? The inside of the globe is coated with a carefully engineered phosphor powder which glows bright white when exposed to the ultraviolet light.
We are even making phosphors which produce ultraviolet light to cure skin diseases.
The possibilities are endless. We can create any color. All we need to figure out is the correct composition of the nanoparticles.
How else is nanotechnology affecting our lives?
We are working to improve the power sources of the future by producing nanoparticles which increase the efficiency of solar cells, saving our planet's limited resources.
Our long-afterglow phosphors may find application one day, lighting up the walls of houses without electricity.
In 1912, over 1,500 people died when a ship which was named Unsinkable hit an iceberg which tore a massive hole in the steel hull. The reason for this has become apparent only with our recent knowledge of how metals behave at the atomic scale. When observing metals at high temperatures, the metal atoms can be seen to move past one another, a process called segregation. By observing metals at the nanoscale, we can learn about their interactions and start to exploit these properties. A small sample of iron is prepared for the nano-SAM. Once the sample is prepared and mounted onto a nano-SAM sample holder, it is placed into the main chamber. A high-energy beam of electrons is aimed at the sample and an image is created by collecting the backscattered electrons. These images can show the placement of atoms at a scale of 5 nanometers, giving incredible detail of how the sample is made up. The image created is like a map showing the placement of individual atoms. This knowledge is being put to work in the development of metal coatings for turbine blades, resulting in stronger, safer, and more durable materials. When the Titanic was built, the steel plates were contaminated with sulfur. The sulfur in the iron caused weak spots which formed breaking points when the ship hit the iceberg at low temperature. With our knowledge of segregation today, the Titanic might still be afloat.
To study particles even smaller than atoms, we can turn once again to the skies. The tiniest building blocks from the birth of the universe, for example photons, still travel through space, and we can observe them with our telescopes.
One of our projects focuses on the Magellanic Clouds, 2 nearby galaxies. We are studying a dying star by observing the X-rays emitted from it.
The potential of nanotechnology is wherever our imaginations take us, and the opportunities are there for those willing to push the boundaries of our knowledge.
The University of Free State Physics Department is just one example of where investment in research infrastructure has yielded fruit. With access to world-class equipment, researchers in South Africa are able to participate in globally competitive research, opening the doors for collaboration with other institutions and industry, both nationally and internationally.
The South African Research Chairs Initiative creates the space for research to flourish. The 150 research chairs awarded across public universities in South Africa build on existing research expertise and contribute towards building a globally competitive knowledge-based economy in which new knowledge results in socio-economic benefits.
We are promoting engagement with nanotechnology through awareness raising, dialogue and education to enable informed decision-making about innovations which seek to improve our quality of life.